June 16, 1944. 32,000 feet above the Kyushu coast of Japan, Technical Sergeant Robert Chen sits in the pressurized fuselage of a B-29 Superfortress, his hands resting on a control grip that looks more like something from a science fiction novel than a weapon of war. He's not in a turret. He's not even looking at the guns he's about to fire. Instead, he's staring through a computing gun sight mounted in front of his face, watching a small illuminated reticle float in space as a Nakajima Ki-84 Frank fighter rolls into attack position 400 yards off the bomber's right side. Chen does something that would have seemed insane to any B-17 or B-24 gunner. He doesn't look at the guns. He doesn't even glance toward the turret. He simply tracks the enemy fighter smoothly through his sight, turns a dial to match the target's wingspan, and when the reticle steadies, he squeezes the trigger. 200 feet away from where he sits, an upper turret he cannot see rotates automatically, elevates precisely, and sends a stream of 50 caliber rounds into empty sky 15 feet ahead of the Japanese fighter's nose. The Frank flies directly into that predetermined killing zone. Tracers chew through the engine, cowling. The fighter shudders, trailing black smoke, and peels away toward the ocean below. Chen never saw the impact, never watched his bullets connect. He just trusted the machine to aim where his eyes could not see, and the machine delivered death with mathematical precision. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was warfare transformed by technology so advanced it seemed like magic. A bomber where gunners controlled weapons they couldn't physically touch. A fire control system that solved deflection equations in real time using nothing but gears, relays, and gyroscopes. A revolution in aerial gunnery that promised to make American bombers untouchable. The promise was extraordinary. The reality would prove far more complicated, because the same technology that could destroy enemy fighters with uncanny accuracy also failed catastrophically when electrical contacts corroded, when wiring harnesses degraded, when vibration threw delicate mechanisms out of alignment, and thousands of young men would learn the hard lesson that bleeding-edge technology rushed into combat doesn't always work the way the engineers promised. The central fire control system aboard the B-29 Superfortress represented the most ambitious attempt yet to solve a problem that had killed thousands of American airmen over Europe and the Pacific. That problem was simple to state but brutally difficult to solve. How do you hit a fighter aircraft moving at 300 miles per hour when your bullets take a third of a second to reach the target and every human instinct screams at you to aim directly at what you can see? By mid-1944, the United States Army Air Forces had learned through bitter experience that traditional gunnery methods didn't work. B-17 and B-24 gunners over Germany, even with computing gun sights like the Mark 14, still achieved hit rates below 20% against crossing targets. Fighter attacks remained the primary cause of bomber losses through most of 1943. The B-17 Flying Fortress and B-24 Liberator carried their gunners in or near the turrets themselves. Ball turret gunners sat between twin 50 caliber machine guns in a cramped sphere underneath the fuselage. Waist gunners stood at open windows, hands gripping weapons directly. Top turret gunners rotated with their guns, physically present between the weapons they controlled. This physical proximity had advantages. A gunner could feel when his guns were tracking smoothly. He could immediately clear a jam by reaching out and manipulating the weapon. If a belt twisted or a shell, casing failed to extract, he was right there to fix it. But physical proximity also created deadly limitations. Those gunners had to endure conditions that eroded combat effectiveness with every passing minute. Ball turret gunners spent hours cramped in a space barely larger than a phone booth, unable to wear a parachute, enduring temperatures that could drop to 40 degrees below zero at altitude. Waist gunners stood at open windows where 300-mile-per-hour winds screamed through the aircraft, freezing exposed skin in seconds, making precise aiming nearly impossible with numb hands. The pressurized cabin was one key innovation. The remote turret system was another. Instead of placing gunners in or near the weapons, The B-29 stationed them at comfortable sighting positions inside the heated, pressurized fuselage. 5 sighting stations total, 1 in the nose for the bombardier, 1 in the upper position behind the flight deck, 2 blister positions on either side of the fuselage where gunners could track targets through plexiglass windows, and 1 in the tail, where a single gunner still sat physically with his guns, the only position that retained the traditional arrangement. These 5 sighting stations controlled 4 remote turrets plus the tail guns: upper forward turret, lower forward turret, upper rear turret, lower rear turret. Each remote turret mounted 2 Browning M250 caliber machine guns. Add the tail position with 2 more 50s plus initially a 20mm cannon, and the B-29 bristled with defensive firepower. 10 machine guns, 12 if you counted the tail cannon, though that would be removed later due to ballistic problems. But the true innovation wasn't just remote control. It was the integration of 5 separate analog computers, 1 dedicated to each sighting station, that calculated firing solutions continuously, while gunners tracked targets. These weren't digital computers. Microchips didn't exist yet. These were electromechanical analog computing devices built by General Electric, assemblies of gears, cams, relays, and servo motors that weighed 200 pounds each and required constant electrical power from the aircraft's generators. Each computer took multiple inputs: range from the gunner's ranging dial, target angular velocity from gyroscopes that measured how fast the turret was tracking, ballistic data for the 50 caliber round, pre-programmed into mechanical cams, air temperature, altitude, and indicated airspeed from the navigator's console. The computer combined these inputs using mechanical resolvers, essentially calculators built from precisely wound coils and rotating shafts, and generated 2 outputs that controlled turret position: azimuth correction, how far left or right the turret needed to point ahead of the target; elevation correction, how far up or down. These corrections were transmitted electrically to motors in the turrets. Amplitude generators boosted the computer's signals to drive the turret's servo motors. The result was a weapon system that aimed itself based on predicted target position rather than current target position. The gunner's job became tracking and ranging rather than aiming. He looked through his computing sight, turned a knob to input the target's wingspan. This automatically set the range when he adjusted a grip to make the reticle's circle of dots span the target's visible size. Then he tracked smoothly for approximately 2 seconds, giving the gyroscopes time to measure angular velocity. The computer solved the deflection equation. The turret moved to the corrected aim point, and when the gunner fired, his bullets met the target in space. In theory, it was brilliant. On paper, it promised hit rates that would revolutionize bomber defense. General Electric engineers and Army Air Force's planners projected that the central fire control system would multiply gunner effectiveness by factors of 3 to 5 compared to manual aiming. Fighter attacks that might have required sustained fire from multiple gunners could be defeated by a single man controlling multiple turrets simultaneously. And there was another advantage. Since one site could control more than one turret through a switching system, the upper gunner, acting as fire control officer, could coordinate defensive fire across the entire bomber. If an attack developed from the right front quarter, the right blister gunner could take control of both the upper forward and upper rear turrets, concentrating 4 50 caliber machine guns on a single target. If a fighter pressed an attack from below, the left and right gunners could both take control of the lower turrets, bringing converging fire to bear. This tactical flexibility had never existed before. B-17 and B-24 formations relied on interlocking fields of fire between adjacent aircraft. Individual bombers had blind spots. German fighter pilots knew these blind spots intimately, developed tactics specifically to exploit them. But a B-29, with its central fire control system operating properly, had almost no blind spots. Nearly every attack angle could be covered by at least 2 turrets, sometimes 4. The testing phase had been promising. At bases in Kansas and Washington state during 1943, B-29 prototype aircraft with early central fire control installations demonstrated remarkable accuracy against towed targets. Gunners with minimal training achieved hit rates above 15%, double what experienced B-17 gunners were achieving in Europe. When General Henry Hap Arnold, commanding general of the Army Air Forces, saw the test footage, he became convinced the B-29's defensive systems would make fighter escort unnecessary. "These big boys can take care of themselves," he reportedly told his staff. The superfortress wouldn't need little friends, the affectionate name bomber crews gave to escorting fighters. It would fight its way to the target and back, relying solely on its own firepower. That confidence influenced strategic planning. The B-29 was designed for very long-range missions, striking targets 1,500 miles from base, but carrying enough fuel for such missions meant reducing defensive ammunition loads or accepting lower bomb tonnage. If the central fire control system worked as promised, commanders reasoned, each bomber could carry fewer total rounds because each round would be more likely to hit. Defensive ammunition could be reduced. Bomb loads could increase. The mathematics of strategic bombing would tilt decisively in America's favor. This optimism permeated training programs. Gunnery schools at Lowry Field in Colorado and Fort Myers in Florida began churning out central fire control gunners starting in late 1943. The training emphasized system operation over traditional marksmanship. Students learned to identify aircraft types by wingspan. They practiced ranging techniques using first models. They spent hours in turret simulators learning to track smoothly rather than in jerks. But the training timeline was compressed. The first B-29 combat missions were scheduled for June 1944, bombing Japan from bases in China. That deadline was non-negotiable. It came from the White House. President Roosevelt wanted American bombs falling on Japanese home islands before the election season intensified. General Arnold, feeling pressure from Washington, pushed production and training schedules to their limits. The result was predictable. B-29 seconds reached operational units with systems that hadn't been fully debugged. Gunners arrived at forward bases with training measured in weeks rather than months. And the first combat missions would reveal exactly how large the gap was between laboratory promise and battlefield reality. The XX Bomber Command, operating from India with forward staging bases in China, represented the first operational deployment of B-29 seconds. Getting the bombers to these bases required an logistical effort so complex it bordered on absurd. Aircraft and supplies flew from India to China over the Himalayas, a route known as the Hump, where mountains exceeded 20,000 feet and weather could kill as efficiently as enemy action. B-29 seconds themselves flew supply missions, stripped of armor and guns, carrying fuel and bombs to Chinese airfields so they could later use those supplies for actual combat missions. It took 7 supply flights to enable 1 combat sortie. This ratio meant the bombing campaign was consuming more resources than it was destroying from the outset. But military logic demanded visible action against Japan. So the missions proceeded despite the arithmetic. June 15, 1944, 75 B-29 seconds, prepared to strike the Yawata Steel Works on Kyushu, the southern island of Japan. This would be the first American bombing raid on Japanese home islands since the Doolittle raid 2 years earlier. And it would be the first combat test of the central fire control system against determined enemy fighters. The mission briefing emphasized defensive tactics. Gunners were instructed to trust their sights, track smoothly. Let the computers calculate the lead. Don't second-guess the reticle position. These instructions sounded simple. Implementation would prove otherwise. Technical Sergeant James Morrison, a right blister gunner on a B-29 named Postage Due, remembered the tension as his aircraft climbed toward cruise altitude over the China Sea. The system checks had gone smoothly. All 5 computers showed green lights. Turrets responded crisply to test inputs. Everything worked perfectly on the ground. But Morrison had been in the Army Air Forces long enough to know that ground tests and combat were different animals. Daylight over Kyushu meant Japanese fighters would see them coming from 50 miles away. Intelligence estimated 60 to 80 interceptors available. Mostly Nakajima Ki, 43. Oscars and Ki, 84 Franks. Fast, maneuverable, and flown by pilots who'd been fighting in China for years. The Japanese had studied captured American aircraft. They knew B-17 and B-24 weak points. They'd developed tactics specifically for attacking bomber formations. What they hadn't faced yet was the B-29. And what American gunners hadn't faced yet was the Central Fire Control System's first real test under combat conditions, where fear, adrenaline, and chaos would challenge every aspect of the human-machine interface. The first attacks developed 90 miles from the target. Small formations of 3 to 5 fighters, diving from altitude, testing the bomber formation's response. Morrison got his first good look at a Frank fighter when one rolled into a beam attack from the right, passing perpendicular to the B-29's flight path at a range he estimated at 400 yards. He centered the target in his sight, turned his ranging grip until the reticle's dots spanned the fighter's wingspan. Tracked for 2 seconds, the upper rear turret, under his control, rotated smoothly. He fired 200 rounds downrange in a 3-second burst, and watched every single tracer pass harmlessly behind the target's tail. The Frank pilot didn't even take evasive action, just kept flying, untouched, while Morrison's ammunition counter spun down. He'd done everything the training manual specified: track smoothly, range correctly, trust the sight. The computer should have been calculating the proper lead. The turret should have been pointing at the intercept point, but his bullets had hit nothing but air. Morrison's experience was being repeated across the formation. Gunners were firing. Computers were calculating. Turrets were moving, and Japanese fighters were flying through the defensive fire largely unscathed. Something was fundamentally wrong, and 75 B-29 seconds deep over enemy territory was exactly the wrong place to diagnose the problem. The issue wasn't immediately obvious. Some turrets were tracking correctly, some gunners were getting hits. Staff Sergeant William Kowalski, in the upper turret position on a B-29 named Devil's Darlin, reported hitting a Nakajima Ki 43 Oscar that attacked head-on, watching his tracers walk up the fighter's fuselage until the engine began trailing smoke. The Oscar broke off, diving away with what looked like fatal damage. But for every success story like Kowalski's, there were 5 or 6 failures. Gunners watching their carefully aimed fire miss by 20, 30, sometimes 50 feet. The computers were supposed to be calculating lead. The turrets were supposed to be pointing at predicted positions. Yet the system was performing barely better than manual aiming, and in some cases worse because gunners had been trained to trust the reticle absolutely, to suppress their natural instinct to adjust aim based on observed results. The post-mission debriefing at the Chinese staging base revealed a disturbing pattern. Out of 75 B-29 seconds dispatched, only 47 actually bombed near the target. Weather and navigation problems scattered the rest. 7 aircraft were lost, 5 to mechanical failures, primarily engine fires that had plagued the B-29 since its first test flights, 2 to enemy action, though Japanese fighter attacks had been fierce and sustained. B-29 gunners claimed 17 enemy aircraft destroyed, 17 confirmed kills out of approximately 80 interceptors that attacked the formation. Japanese records would later show actual losses closer to 4 fighters. The overclaiming wasn't unique to B-29 crews. All bomber formations overclaimed. Multiple gunners fired at the same targets. Combat happened at speeds that made accurate observation impossible. A smoking fighter breaking away might recover and limp home, but the gunner who hit it would claim a kill. What alarmed the intelligence officers analyzing the mission wasn't the overclaiming, it was the ammunition. Expenditure. The 75 B-29 seconds had carried approximately 400,000 rounds of 50 caliber ammunition total. They'd fired roughly 180,000 rounds in combat, and those 180,000 rounds had yielded, at most, 4 confirmed enemy aircraft destroyed. That was 45,000 rounds per kill. By comparison, B-17 formations over Germany in early 1944 were averaging approximately 25,000 rounds per confirmed fighter destroyed. The B-29, with its revolutionary central fire control system, was performing worse than the aircraft it was designed to replace. The problem had to be identified fast because more missions were already scheduled. The entire strategic bombing campaign against Japan depended on the B-29 working as promised. But working required understanding why it wasn't working, and understanding required peeling back layers of complexity that went far beyond what most maintenance crews and gunnery instructors had been prepared to handle. The Central Fire Control System's sophistication was its greatest strength and its greatest vulnerability. When every component functioned correctly, the system demonstrated capabilities no other bomber could match, but it required that every component function correctly, simultaneously, continuously. And the system had roughly 15,000 individual parts across its 5 computers, amplifier units, servo motors, turret drives, electrical harnesses, and control panels. 15,000 parts meant 15,000 potential failure points, and the B-29 had been rushed into production so aggressively that many of those parts hadn't been adequately tested under actual combat conditions. High-altitude cold, vibration from 4 massive radial engines, electrical interference from radar systems, corrosion from humidity in tropical staging bases, dust contamination from primitive Chinese airfields where maintenance happened in open air. The first major problem identified involved the electrical wiring harnesses. General Electric had designed the system with complex wiring bundles running from the computers to the turrets, sometimes spanning 70 feet through the fuselage. These bundles contained dozens of individual wires, each carrying specific signals: azimuth command to the turret, elevation command, power supply, feedback signals confirming turret position. The wiring harnesses were supposed to be shielded against electrical interference and protected against chafing. But wartime manufacturing shortcuts and the desperate push to meet production quotas meant quality control failures. Some harnesses left the factory with inadequate shielding. Others were damaged during installation as mechanics wrestled them through the crowded fuselage. And once installed, the harnesses were subjected to vibration and flexing that no laboratory test had accurately simulated. When wiring insulation degraded, bare conductors could touch, creating short circuits. A signal meant to command the turret left might instead command it up, or the turret might receive conflicting signals and begin slewing wildly, hunting for a position it could never reach because the computer was telling it to do impossible things. The most catastrophic failure mode became known as runaway turret syndrome. A short in the wiring harness would cause the turret to spin to a hard stop, usually about 20 degrees from its last commanded position, and then fire its entire ammunition load in that direction. 1,000 rounds of 50 caliber ammunition, discharged uncontrolled, in roughly 8 seconds. If that direction happened to point at another part of the aircraft, the results were obvious. Multiple B-29 seconds suffered serious damage from their own guns. In a few nightmarish cases, runaway turrets fired through the fuselage, killing crew members. One aircraft lost its tail gunner when an upper turret malfunctioned and fired directly aft, through the pressurized fuselage. The tail gunner never had a chance. By the time the system could be shut down, he was dead at his station. This failure mode terrified crews. They could accept being shot down by enemy fighters. That was the nature of combat, but being killed by their own malfunctioning guns felt like betrayal. Trust in the Central Fire Control System began eroding not because it failed to hit enemy aircraft, but because it sometimes tried to kill the men it was supposed to protect. General Electric engineers, working desperately to diagnose the problem, eventually traced the runaway turret issue to a combination of factors: poor quality control in wiring harness manufacture, inadequate circuit protection, and a design flaw in the computer's relay logic that failed to include sufficient safeguards against invalid signal combinations. The fix required rewiring portions of the system and installing additional circuit breakers. But implementing the fix across the B-29, the fleet required time measured in months. And combat missions continued because strategic imperatives didn't pause for engineering problems. So crews flew with systems they knew were potentially deadly, praying the failures would happen to someone else's aircraft. The wiring problem wasn't the only issue. The computers themselves proved fragile under combat conditions. Each unit contained approximately 800 relays, electromechanical switches that opened and closed electrical circuits. These relays were supposed to be ruggedized for military service, but ruggedized in 1944 meant something different than it would mean in later decades. The relays could fail due to dirt contamination. They could fail due to corrosion on the contacts. They could fail due to mechanical fatigue after thousands of switching cycles. And when relays failed, the computer's calculations became unreliable or stopped entirely. Some computers developed intermittent faults that were nearly impossible to diagnose. A computer might work perfectly during pre-flight checks, fail during the mission, then work again during post-flight testing. Maintenance crews called these ghosts in the machine. The computer would pass every diagnostic test on the ground but fail in combat when it mattered most. Part of the problem was environmental. The computers were designed to operate in pressurized, temperature-controlled compartments. But pressurization sometimes failed. Electrical heaters sometimes quit. Temperature swings from ground-level heat to high-altitude, cold, stressed the mechanical components. Solder joints cracked. Lubricants became either too thick or too thin. Precision gear assemblies developed backlash that introduced errors into the calculations. And there was another problem that no amount of engineering could easily fix. The system required constant calibration. Range inputs had to be accurate. The ranging reticle in the gun sight was supposed to span the target's wingspan precisely when the gunner adjusted the range grip. But gunners had to estimate target wingspan first, inputting the value manually. Japanese fighters came in multiple types with different dimensions. A Mitsubishi, a 6M0, had a wingspan of 39 feet. A Nakajima Ki 84 Frank spanned 36 feet. A Kawasaki Ki 61 Tony measured 39 feet. In combat, with fighters attacking at high speed from multiple angles, gunners had seconds to identify aircraft type and input the correct wingspan. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Mistakes were inevitable. A gunner who input 36 feet for a 0 was giving the computer incorrect range data. The computer would calculate lead based on the wrong range, commanding the turret to point at an intercept position that didn't match reality. The bullets would miss. And the gunner, trusting the system, wouldn't understand why. Some gunners learned to compensate. They'd input wingspan values slightly off from actual, creating systematic errors that counteracted other errors in the system. This worked for individuals who'd flown enough missions to develop intuition about what worked. But it defeated the entire purpose of having a computing system. If gunners had to intuitively adjust inputs to get the computer to produce correct outputs, you might as well abandon the computer and go back to manual aiming. The parallax problem added another layer of complexity. Parallax is the apparent shift in position of an object when viewed from different locations. In a B-29, the sighting stations were separated from the turrets by significant distances. The upper gunner's sight might be 15 feet aft of the upper forward turret. The right blister gunner might be 20 feet away from the turret he was controlling. This separation meant the gunner's line of sight to the target was different from the gun's line of sight. The computer had to correct for this parallax, calculating how much the turret needed to be offset to make the gun's line of fire intersect with the gunner's line of sight at the target's range. This correction changed depending on target range and angle. Close targets required more parallax correction than distant targets. Targets directly ahead or directly behind required less correction than targets to the side. The central fire control computers included parallax correction in their calculations, but the correction depended on accurate range input. If range was wrong, parallax correction was wrong, and the error compounded the existing deflection error. The result could be bullets missing by dozens of feet, despite the gunner doing everything correctly from his perspective. By August 1944, after 2 months of combat operations from China, the central fire control system's problems were well documented. Mission reports piled up at XX, Bomber Command headquarters detailing malfunctions, failures, and disappointing hit rates. But solutions remained elusive. The system was too complex to fix quickly, too interdependent to patch incrementally. Every attempted fix in one area seemed to create new problems elsewhere. And then Curtis LeMay arrived. Major General Curtis Emerson LeMay took command of XX Bomber Command on August 29, 1944. He was 40 years old, a combat veteran who'd led bomber groups over Europe, and a man with a reputation for brutal pragmatism. LeMay didn't care about elegant engineering or revolutionary technology. He cared about bombs on target and crews coming home. LeMay personally flew combat missions as an observer, sitting in jump seats behind pilots, watching how crews actually operated under fire. What he saw alarmed him. Gunners were fighting their own equipment as much as they were fighting enemy aircraft. Time that should have been spent tracking targets was being spent troubleshooting computer malfunctions or manually taking over turret control when the automation failed. He ordered a comprehensive analysis of gun camera footage from recent missions. The analysis confirmed what he'd suspected. When the central fire control system worked correctly, it demonstrated excellent accuracy. Hit rates approached 25% against crossing targets, better than anything B-17 or B-24 gunners achieved. But the system worked correctly less than half the time. And when it failed, it often failed catastrophically in ways that degraded performance below manual aiming. LeMay made a controversial decision. He ordered maintenance crews to aggressively troubleshoot and repair central fire control systems, but he also authorized gunners to switch to manual backup mode at their discretion. Each sighting station had a computer switch. In meant the computer was controlling turret aiming. Out meant the turret simply slaved to follow where the gunner pointed, his sight, with no computing corrections. Previous doctrine had discouraged using the OUT position except in emergencies. The official guidance emphasized trusting the computer. But LeMay understood that trust had to be earned through performance. If a gunner noticed his computer producing bad solutions, he should be empowered to bypass it rather than continuing to fire at positions the computer incorrectly calculated. This hybrid approach, experienced gunners using the computer when it worked, switching to manual when it didn't, produced better results. Hit rates didn't increase dramatically. The human gunner shooting manually still struggled with deflection shooting, but at least they weren't being actively misled by faulty computation. And morale improved because gunners felt they had control rather than being passive operators of unreliable automation. The maintenance problems persisted. Spare parts were chronically short. The exotic components in the central fire control, computers weren't stocked in sufficient quantities at forward bases. When a computer failed, mechanics sometimes had to cannibalize parts from other aircraft, creating a cascade where fixing one bomber broke another. And the hostile operating environment degraded systems faster than anyone had predicted. Chinese airfields were primitive. Maintenance happened in open-air revetments where dust storms could bury aircraft in hours. Monsoon rains turned airfields into mud. The dust got into everything: electrical contacts, relay assemblies, servo motor bearings. Mechanics did their best with inadequate tools and insufficient facilities, but they were fighting entropy itself. By late 1944, the strategic picture was changing. The capture of the Mariana Islands, Saipan, Tinian, and Guam provided better bases closer to Japan. The entire B-29 effort began shifting from the China-Burma-India theater to the Marianas. New aircraft arriving in the Pacific incorporated fixes to the most critical central fire control problems. Wiring harnesses had better shielding. Circuit protection was improved. Relay quality control was stricter, and crews arriving in the Marianas had better training. The early compressed training programs that sent gunners to China with just weeks of preparation had been extended. By 1945, B-29 gunners were receiving 3 months of training focused heavily on central fire control system operation. They learned not just how to use the system, but how to recognize common failure modes and switch to backup operation gracefully. The XXI Bomber Command, operating from the Marianas starting in November 1944, represented the central fire control system's second chance. Missions against Japan from the Marianas were shorter than missions from China, 1,500 miles round trip instead of 3,000. That meant less time for systems to fail, less vibration exposure, less opportunity for the complex electronics to malfunction. And Japanese fighter opposition, while fierce, was beginning to weaken. By early 1945, Japan's pilot training program had collapsed under the weight of combat losses. Many interceptors were flown by pilots with minimal experience. These pilots made tactical errors that even partially functioning central fire control systems could exploit. A novice pilot flying straight and level for a few seconds was a much easier target than a veteran fighter pilot who varied his speed and angle continuously. The statistical evidence from Mariana-based operations showed improvement. B-29 gunners claimed 714 enemy aircraft destroyed during the entire Marianas campaign. Japanese records suggest actual losses were significantly lower, probably around 300 aircraft, but even that lower number represented effective defensive fire. The central fire control system, when it worked, was contributing to force protection. But the ultimate verdict on the system came from Curtis LeMay, in a decision that shocked the bomber community. In February 1945, LeMay ordered most defensive armament removed from B-29 seconds for low-altitude night incendiary missions. The change was driven by tactical considerations. Low-altitude missions at night meant Japanese radar-directed fighters struggled to intercept. The few fighters that did make contact attacked from below, where the central fire control system's lower turrets had the best coverage. So LeMay kept the tail guns, and sometimes one or two of the remote turrets, but removed the rest. The weight savings allowed bombers to carry more fuel and more bombs. And critically, removing the guns removed the central fire control computers, the wiring harnesses, the servo motors, all the complex systems that required constant maintenance and frequently failed. Aircraft flew lighter. Maintenance crews had fewer systems to troubleshoot. Mission reliability improved. The decision implicitly acknowledged what everyone already knew. The Central Fire Control System, in its World War II implementation, had never lived up to its promise. When it worked brilliantly. But it worked reliably only under conditions that rarely existed in combat. The vision of B-29 seconds fighting their way to targets solely through defensive firepower, with no fighter escort needed, had proven false. Yet the system wasn't a complete failure. Its existence forced Japanese fighters to respect B-29 formations. Pilots who'd aggressively attacked B-17 seconds and B-24 seconds approached B-29 seconds more cautiously, knowing that accurate fire could come from unexpected angles. That caution saved bomber crews, even when the central fire control system wasn't actively shooting fighters down. The deterrent effect had value, and the technological lessons learned proved invaluable. The problems identified during B-29 operations, wiring reliability, computer ruggedization, human-machine interface challenges, informed next-generation fire control systems. The B-29's derivative, the B-50, incorporated improved central fire control components based on wartime experience. And by the Korean War, when B-29 seconds faced MiG-15 jet fighters, the systems had been refined enough to achieve some success despite being fundamentally obsolete against jets flying at 600 miles per hour. Part 3. Final section. The broader lesson transcended specific technical problems. The central fire control system represented an attempt to use automation to overcome human limitations. Gunners couldn't calculate deflection angles fast enough consciously, so build a machine to do the calculation. Gunners couldn't maintain steady tracking under stress, so build servo systems to stabilize the turrets. Gunners couldn't be in multiple places at once, so build remote controls that let one man command multiple weapons. Every element of that vision was sound in principle, but principles had to survive contact with reality. And reality, in 1944, meant manufacturing processes that couldn't yet build sufficiently reliable components, maintenance procedures that hadn't been developed for such complex systems, training programs that couldn't fully prepare operators for the cognitive demands of human-machine cooperation under combat stress. The gunners who learned to work effectively with the central fire control system developed a particular kind of expertise. They understood the technology well enough to recognize when it was functioning correctly and when it was lying to them. They could switch fluidly between automated and manual modes. They'd internalized the system's quirks, knowing that this particular computer tended to overcorrect in azimuth, or that particular turret had bearing slop that introduced lag in elevation. This expertise couldn't be taught in classroom settings. It emerged from experience, from flying mission after mission, from that moment when a gunner realized the reticle was pointing at an obviously wrong position, and his trained intuition screamed to ignore it. The best gunners became collaborators with the technology rather than servants of it. They used automation as a tool, but never surrendered judgment to it. The automation itself continued evolving long after World War II ended. The B-52 Stratofortress, entering service in the 1950s, carried a tail turret controlled by a computing system that was essentially a digital descendant of the B-29's analog computers. But by then, the technology had matured. Solid-state electronics replaced relays. Digital logic replaced mechanical resolvers. And 50 years of engineering refinement had eliminated most of the reliability problems that plagued the original system. Modern military aircraft take the concept to its logical conclusion. The AH-64 Apache helicopter gunner aims a 30mm chain gun by moving his head. A helmet-mounted sight tracks where he looks. The gun follows. Ballistic. Computers solve deflection in microseconds. The gunner doesn't even think about lead angles. He looks at the target, designates it, and the machine handles everything else. Fighter aircraft went further still, removing human gunners entirely from the equation. An F-22 Raptor's gun system uses radar tracking, inertial sensors, and digital fire control computers processing millions of calculations per second. The pilot designates a target. The computer determines if guns are appropriate. If so, it calculates the intercept point and displays an aiming cue. The pilot maneuvers to put the target in the queue and fires. The entire deflection problem that killed thousands of bomber gunners is solved automatically, invisibly, faster than conscious thought. But those modern systems exist because engineers in the 1940s tried to solve the same problem with the technology available to them. The central fire control system was crude by contemporary standards. Its computers were slower than modern calculators. Its electrical systems were fragile. Its human interface was poorly designed. Yet it represented a genuine attempt to transcend human limitations through machine intelligence. The men who flew with it, who trusted it when it worked and fought it when it failed, were pioneers in human-machine cooperation. They learned lessons about automation that remain relevant 80 years later. Technology can enhance human capability, but only when it's reliable enough to trust. Automation should assist judgment, not replace it. And the most effective systems are those that keep humans in control while offloading specific tasks machines can handle better. The B-29 gunners who started firing without looking, trusting a computer to aim weapons they couldn't see, were doing something profoundly unnatural. Every instinct said to look at your guns, to watch where your bullets went, to correct your aim based on observed results. The central fire control system demanded they suppress those instincts and trust mathematics embedded in gears and relays. Sometimes that trust was rewarded. Japanese fighters tumbling from the sky, hit by bullets that followed trajectories no human gunner could have calculated consciously. Other times that trust was betrayed. Malfunctioning computers, sending turrets spinning uselessly, while enemy fighters pressed their attacks unopposed. The system promised 5 times better performance than manual aiming. It delivered maybe twice as good, and only when everything worked correctly, which was less than half the time in actual combat operations. That gap between promise and reality defined the central fire control system's legacy. Not a failure, because it did work often enough to contribute to the war effort. Not a success, because it never achieved what its creators envisioned. Instead, it existed in the uncomfortable middle ground where most revolutionary technology lives during its early deployment. The engineers learned what didn't work. Maintenance crews learned what couldn't be adequately serviced in field conditions. Trainers learned what couldn't be taught in accelerated programs. And gunners learned that automation, however advanced, was a tool that required human judgment to wield effectively. Those lessons fed directly into post-war fire control development, the systems that protect modern aircraft, that guide modern weapons, that enable modern precision, all descend from the imperfect, ambitious central fire control system that General Electric built for the B-29 Superfortress. The gunners who flew with it rarely spoke about the technical details after the war. They remembered the missions, the fear, the camaraderie, the violence. The computers and turrets and servo motors faded into the background of memory, just parts of the aircraft like wings or engines. But their experience using those systems shaped military technology in ways they never fully recognized. They proved that humans and machines could work together in combat, even when the machines were primitive and unreliable. They demonstrated that automation could enhance warfare effectiveness, but only when properly implemented and supported, and they learned, sometimes at terrible cost, that trust in technology must be earned through performance, rather than assumed based on promises. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.